Okay. So collisions, specifically talking about energy and momentum. Very obviously, a collision is when two things run into each other, or one thing runs into a wall, or multiple things run into each other, whatever. And when that happens, there's a transfer of energy. So if you haven't seen this already, I'm sure you will see it very, very soon. Things have energy. And the thing that we're going to be looking at right now is something called kinetic energy, which is the energy that something gets from moving. So let's say you have a ball that is moving in this direction. The ball has some mass, we're going to call it m, and it has some velocity v. Note that I've written this v with like a funny little hat on top of it. This is the notation to show that something is a vector. And I think we talked about this at some point in time before, but I'll go over it again because it's way more important here. A vector consists of a magnitude, so let's call this 10 meters per second, and a direction. So in this case, to the right. This is a vector. Something could be 10 meters per second up, 10 meters per second down. If we drew this a second time in this direction with a v prime, we could either say that this is like 5 meters per second to the left, and this is the way that you'll mostly see it, but you could also say that this is -5 meters per second to the right. This is a weird notation, but you're gonna have to start getting used to it, because if the right is our positive direction, then the left is our negative direction. It's speed, which is not the same thing as velocity. A lot of times you'll see speed with like the absolute value marker. So for v, it would be 10 meters per second. And then for the one down here, the v prime would be 5 meters per second. No matter what direction, because it is moving at that speed. When we're talking about velocity, to the left or like negative to the right, very, very, very important. And make sure you know this. And then I say that, but then we're also talking about energy. So if something is moving, and let's just erase the other stuff, 10 meters per second to the right, then that also means that it has a kinetic energy associated with it. And the equation that you can use to find that, you will see it sometimes as Ke, sometimes you'll just see it as K, sometimes you'll see it as T. But the equation for this is 1/2 mv squared. Note that there's no vector notation for this v. In the like physics version of this, when you square a vector by itself, it is no longer a vector. And so direction for the kinetic energy does not matter. But let's say the mass of it is 5 kilograms. Its energy would be 1/2, and I'll plug these in, 5 kilograms, and then 10 meters per second quantity squared. So I'm going to get 250 kilogram meters squared per second squared. This unit right here, kilogram meter squared per second squared, is also known as a joule. You'll see it written as just a J though. These are the units of energy. So if something has a mass and is moving with some velocity, this is how you can find its kinetic energy. If an object is moving and it impacts with another object right here, and then bounces back off, then there is something called a transfer of energy. Most of the time in real life, some of the energy will be lost. There will be a sound, there'll be some friction, some heat, an explosion or something, but energy is mostly lost. However, you guys have probably heard something called the conservation of energy. What this means is that there's no energy created, nor is it destroyed. It just goes somewhere else. So in an inelastic collision, say you take like a ball made out of metal and you throw it at the wall, it's going to make a huge sound. It's not going to come back quite as quickly. That is an inelastic collision. There's still a conservation of energy. All the energy that you put in to that thing as you throw it comes back out. But most of that comes back out as like a sound or heat or whatever, and only a small amount of it comes back as velocity. However, if there's something that is an elastic collision, this is the bounciest of bouncy balls of all time. You throw it at a wall, there is no sound involved, no heat is produced. All of the energy that went into throwing the ball is returned as it bounces off. In this case only, the initial kinetic energy is equal to the final kinetic energy. If it is not an elastic collision, and sometimes you'll see it as like a 100% elastic collision, then you can't use this relation right here. Yeah. Let's see. I don't think I need to say anything about this. If there are two objects moving, so you have object 1, and then it's moving like this, and then you have object 2, and it's moving like this, there is a total kinetic energy associated with this. So there's like a total kinetic energy of the system. And the way that you would do that is just by doing kinetic energy 1 plus kinetic energy 2. And then you can look at that from the initial and the final. If it is a 100% elastic collision, then the sum of these two right here will be equal to the final and the initial. And these are for the totals. Okay, so that's energy. It is important to know. We're going to be doing another lab that uses energy a lot more. But for this week, the main thing we need to focus on is momentum. Momentum is super important. In fact, Newton's second law, the F is equal to ma, is actually a simplification. We see that F is equal to ma, and we'll put our vector quantities because force and acceleration are vectors. This right here is not entirely true because this is assuming that the mass is always constant, which is not always true. It will be true for all of your problems, but the official way to write force is the time derivative of the momentum. Which means that we can sort of like look at this because we know that momentum, or I guess I'll tell you that momentum is equal to mass times velocity. And notice that these are vector quantities. The direction for the velocity and the direction for the momentum matter a lot. If we take the time derivative of this and mass is constant, so if we do d by dt of mv and the mass is constant, the mass can come out. We just get dv by dt, which is equal to ma. But if the mass is not constant, if the mass is changing, like if you're in a rocket ship or something and it's expelling fuel down, so it's losing mass, then you can't use f of as equal to ma. When we're talking about collisions, momentum is always, is that p power or momentum? That is momentum. It's usually written with a lowercase p. Power is usually written with an uppercase p. And it's hard when you're writing to tell the difference, but usually you'll be able to know just by like context clues. I'm going to say this 3 times so you understand me. Momentum is always conserved in a collision. Momentum is always conserved in a collision. Momentum is always conserved in a collision. So say we have an object going here and then an object that's going this direction, but a little bit slower. This has m1, v1, and we'll call this m2, v2. That is what the momentum of these objects are. And again, I will draw them with the vector hats because that is important. We can see that this object right here is going to catch up to this object, and then after some amount of time, we will have 2 objects moving at some v3. We can calculate the momentum of this total object because m3 is just going to be equal to m1 plus m2. So the momentum of object 3 is going to be equal to m1 plus m2 times v3. P3 right here must be equal to, so I'll say this, P3 must be equal to m1 v1 plus m2 v2. This will always be true. Even if the object is moving, initially in this direction, then you would just have a negative velocity to start out with. And this would still be true. There will never be a situation where 2 objects combine and the total momentum of the system is different. Notice that is talking about the whole system. So we're talking about this right here, P1 plus P2, and then we're talking about the combined system, P3. We're not talking about anything else. There will be situations, and particularly in this lab, where you have an object that's bouncing off of a wall. This wall is not part of our system. The only system that we're looking at is the ball right here with its m1, v1. So here's where I give you guys the hint / kind of one of the answers. If this ball is traveling, let's say it has a mass of 10 kilograms and is traveling initially at a velocity of 2 meters per second. I want you to just think to yourself, what is the momentum of this object? What is the initial momentum of this object? Should be easy, right? 20. Let's say it bounces off and now its velocity is -2 meters per second. What is its momentum now? If you said -20, you are correct. Its momentum after the fact, its P final, is equal to -20 kilogram meters per second. This is the unit, and this is as simplified as it gets. The negative is so important, you guys. It's so important. This tells us what direction it is going in. If we have set up our coordinate system, nothing is stopping us from making the right direction our initial negative right here. But then that would mean that our initial velocity is -2 and that our final velocity is +2. But we're not going to do that just because it's a little bit confusing for us here. Okay, so if our initial momentum, was equal to 20 kilogram meters per second, and our final momentum is equal to -20 kilogram meters per second, what is the delta P? What is the change in momentum? So take 20 seconds, think to yourself. So remember that the change in something is equal to its final minus its initial. That is how much it has changed by since it started. And so if we plug things in, we have -20 minus 20 is equal to -40. That is the correct answer. The negative is very, very important because, again, it tells us direction. It tells us, okay, it was going in the positive direction, and then now it's going in the negative direction, which means it has to have been pulled back or pushed back or whatever in the opposite direction. And so the delta is -40 kilogram meters per second. Okay, what if we have that same situation where the ball is impacting with a wall? It has M1, V1, and then when it hits the wall, it's made out of, like, I don't know, really gummy material, and it sticks, so that our V2 is equal to 0. The momentum before, and let's say that we're doing the same thing as before, so the M1 is 10 kilograms, and then the V1 is 2 meters per second. What is the delta P here? Think to yourself for just 2 minutes. I say 2 minutes, it's not going to take you that long. The P final can be written as M1 V2 because it's the same mass, minus the initial, which was M1 V1. So I'll plug in my values. I've got 10 times 0 minus 10 times 2. So this is 0 minus 20, -20 kilogram meters per second. It was going at a momentum of 20 kilogram meters per second, and then it was stopped. So that means 20 of those units had to be taken out. This is what the change in momentum of a particular object is. So a single object can indeed gain and lose momentum. And in fact, if we set up our situation again with two objects colliding with one another, P1 is not going to equal to P1 prime. After it has bounced off, that's not going to be the same. Same thing with here. P2 is not going to be the same as P2 prime. Their individual momentums are going to change. But the thing that we care about is that P1 plus P2 is equal to P1 prime plus P2 prime. And this will always be true today, tomorrow, a million years from now. This is the important concept. If you can't understand this right here, then you're going to miss a lot of points. So why don't we take a look at the actual simulation? I'll pause for a second. When you follow the link in the lab booklet, you'll come to this page right here. The only one of these four that we will be using for the main part is the exploring one dimension. We're only going to be looking at collisions in one dimension. The first thing that you should do when you come to this page is to click on more data, because we care more about just the mass. We can see the velocity and the momentum of each of the objects. Another thing that I would recommend that you do is click on kinetic energy and momentum. You will see vectors. These are, magnitude and direction. These will show the relative values of each one of those. You'll start by only using one ball. You can set its position by clicking and dragging, or you can click here and set it with this onboard calculator. Same thing with the velocity. I can set it to 2. I can set the mass to 10. No, I can't. It has to be between 0.1 and 3. So 3. And then I can look at the situation. Okay, its initial is 2. Its initial momentum is 6. I can run the simulation, and it bounces off, and the values have just changed to the negative values. And we look over here, the elasticity is 100. That's what we would expect. And if we turn this down to, say, 50, we can see that now it's going slower. Its momentum has decreased. But if we put in, let's make this a positive 1. If we put in a second ball going in the opposite direction, why don't I make this equal to 2? We can see that the initial momentum of the first one is 3. The initial momentum of the second one is -1. So take 2 seconds. What is the total momentum of the system before the collision? And actually, I want you guys to put it into the chat. I want to see if you guys can tell me what it is. We have one answer. Okay. We have 3 answers out of the, 13 people we have here. I hope those people who are not answering are still paying attention. The answer is 2. Because, it's very easy. You can look, the momentum 3 minus 1 is equal to 2. Because we have P1 plus P2 is 2. After the collision, what should the total momentum be? In this one, yeah. The momentum after this collision should be the same. So if I run the simulation and then pause right after, we can see that each individual momentum has changed. The big object is now just going at, has a momentum of 0.3, and the other one has a momentum of 1.7. But when you add those up together again, you should get 2. No matter what the elasticity is of this situation, if I turn this down to 0, it's the same. If I turn it up to 100, it's the same. But if you look here in the bottom left-hand corner of the actual simulation, and this is the worst place to put it, the kinetic energy will change. So this one, it starts at 1.75. If the elasticity is 45%, the kinetic energy changes. If it's at 0%, I lost it. Okay. The only time it will stay the same is if it is at 100%. I know that this, like, it feels like I'm just saying the same thing over and over and over and over again. And I hope that's not too annoying because it's super important. And that's why I'm saying it over and over and over again.